Hi everyone, my name is Thomas Kim. Today is November 24th, 2019. This is my 35th episode about linear algebra and threading building blocks. In this episode, I will discuss C++17 lock-free parallel algorithm. We should avoid using atomic and mutex or lock in parallel algorithm. Instead, we should use thread local storage or STD transform reduce parallel algorithm. For more information about transform reduce, please double click this link. Transform reduce is introduced in C++17 standard. Especially, we are interested in this syntax. I will copy the syntax and paste it for your reference. Please note that this episode is based on episode 24. If you haven't watched this episode, please double click this link and watch this episode. Otherwise, you cannot understand my current session. Also, I will post this script in the description section below. Please double click this link to download previous source code. Show in folder, unzip the folder, right click, rename, 35, reduce, index, algorithm. Hit enter, double click the folder. I will remove addition.cpp, complex.cpp, typevector.cpp, profiling.cpp, delete. Now copy the folder, paste it to your working folder. This is my working folder. Paste. Start Visual Studio Code. Open your folder. Expand folder 35. Double click transpose. Ctrl V. Ctrl N. Here. Void test. Transform. Reduce. Copy the function name. Paste it here. We will delete up to this point. Now, using element T double std vector element T b 1/3.0 2, 3, 4, 5, 6, 7, 8, 9, 10 or sum up or A or B, return A plus B. I will define another one, or handle parallel or element, return element, or sum, std, transform, reduce, std, execution, par unsequential, b, begin, b, end. We provide initial value element T, the containers element type. Then we provide sum up, it takes 2 arguments. Then we provide handle parallel, stream, sum of B is sum, and there. Sorry, fix like this. Now start command prompt, dir cd 35, reduce, index, algorithm, dir, clang ++ std, C++17, The file name is transpose.cpp, transpose.cpp, ltbb, ltbb malloc. Hit enter. cls. Okay, this is the result of all summation. Now I will copy once again. Copy, paste. I will change it to analyze. Copy this function name, paste it here, disable it. Now here, using mutex t, TBB, spin mutex, mutex t, mutex, auto, stream, this is global stream, auto, and there, and there. Now put it here, also put it here, we capture all, create a block, mutex t, scoped lock, mutex, stream, sum of A, B, and there. Now copy this part once again, paste. This is handle, parallel, L. We are calling this function from here. Build again, cls. So in this case, handle parallel 0.333, 0.333, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in this block, L is the value of each element. It is not index, not iterator. L is the reference value of the iterator, or the element of the container. But in our linear algebra algorithm, we need the index, not the reference value. So I will copy this, copy, paste. I will modify like this, indexed, transform. I will copy this function, copy, and paste it here, disable it. Please understand that there are two big drawbacks in the C++ standard parallel algorithms. One is that the parallel algorithm returns the referenced value of the container. The other is that exceptions cannot be leaked from the parallel body of the algorithm. Now scroll down. I will delete this part, and in this part, now this is index, size t, index. Now I can delete this. From this vector, the index, and the sum of argument type is element t and element t. Now here, for counting iterator, size t, for counting iterator, size t, B size. So we can delete these two parts. Now the remainder is the same. Now in the command prompt, hit enter, CLS. It works exactly the same. Please note that we are calling indexed transform reduce. You have to understand this syntax. I will now delete this part. Please understand this concept. I will build once again. CLS. About counting iterator, these are defined iterator.h or parallel HPP here. About counting iterator, I explained in episode 24. So if you haven't watched episode 24, you should have watched episode 24 if you want to understand counting iterator. Now we will use this algorithm and create a library. Copy this block, paste, change it to reduce index. I will create another type name, sum of type, copy, sum of type, sum of. Also we need another type name, init type, init type, init. And instead of callback, I say parallel callback type. Copy, paste. No. I say handle parallel type. Copy this, copy this. Say handle parallel. And return type should be auto. Now with this, instead of this, delete std transform reduce std execution par unsequential counting begin counting end init. I say init value, then sum up, then handle parallel std forward sum of type std forward handle parallel type we have to fix like this. Now we have to return. Now copy this part, copy, paste. Now it should be sequenced. I will copy once again, copy, paste. Now here, container type. I will delete this part, container type, container, copy container, size, it can be 0, and we don't need this. It can be container size. Now remainder is the same. I will arrange it like this. And also here, like this. With this, now I copy once again, paste, test reduce index. Now instead of doing this, par reduce index, size t, b size, now I modified like this. We call this function copy, paste. Now in the command prompt, CLS, okay, it works perfectly. I will copy once again, copy, paste, test reduce index, container. Then instead of doing this, we can just pass v. Then I copy this, copy, paste, hit enter, CLS, it also works. In episode 14, log-free synchronization and parallel Leibniz determinant. In this video, we implemented determinant Leibniz parallel using atomic. Now, matrix 2D HPP. Here, I will copy the same code, pasted, determinant Leibniz, reduce index. I changed the function name. Now in this block, I will remove this part. Scroll down. From here, I will remove up to this point. Scroll up. I will unindent Now I will delete det and like this. Now I will delete this part. Now I turn it, handle, parallel. Now we have to return partial det. We are returning this partial value. Scroll down. We need to create auto sum up, auto A, auto B, return A plus B. Now here, return var reduce index size t. We are providing this number. Initial value will be element type, then sum up, then handle parallel. So we implemented this function. Here we are using this parallel algorithm using transform reduce. Now in transpose, scroll up, test matrix Hermitian, determinant of A using A determinant, Leibniz serial, and L Leibniz serial. I will copy once again. Determinant of A using determinant Leibniz reduce index. We just implemented this determinant. I copy once again. Copy, paste, determinant of B. I will use another algorithm. Determinant Laplace reduce. It should be B. Laplace reduce. Determinant of B using Laplace reduce index. Determinant Laplace reduce index. We haven't made this function yet. It should be B. Determinant Laplace atomic. Right click, go to definition, copy, paste, determinant Laplace reduce index. Now scroll down. We don't need atomic. I delete. We don't need spin. I deleted mutex. I will delete this part. And I will also delete this part. I will delete this part. Cut. Paste. I say partial dt, paste. I change it like this. We don't need this part. return partial det. Now we don't need this. Or sum up or A or B, return A plus B, return par reduce index it should be size T, element type, sum up. Now we delete this. So in this algorithm, we have not used atomic, we have not used log. This is determinant Laplace reduced index. Now here, determinant Laplace reduced index. Now let's build. $621 say partial det. Copy, 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 copy. $610. Sorry. It should be J. I delete this. Delete this. I don't need this. Return hit enter. Okay, CLS. We enable this function, test Hermitian, paste. We disable it, build again, CLS. So determinant of A using Leibniz serial 80-115, Leibniz reduce index the same. Using determinant of B using Laplace reduce 80-115 minus 115, Laplace reduce index 80 minus 115. So identical. Please understand that STD transform reduce parallel algorithm is introduced in C++17. To understand this algorithm, as I explained in this episode, you should have watched my previous episode 24. After watching this episode, if you watch my current video, you may better understand my current episode. If exception of a function invoked as part of the algorithm throws an exception and the execution policy is one of the standard policy, STD terminate is called. For any other execution policy, the behavior is implementation defined. It means in this parallel body, also in this body, exception should not be thrown. Otherwise, your application crashes. In future episodes, we will use this reduced index algorithm from time to time. In my next episode, I will discuss linear independence and linear dependence. Please subscribe to my YouTube channel. Thank you for watching.